Hi, Algebra 2 honor students. This is going to be your fourth day of Unit 3. We're on page 15 in the packet talking about problem solving with transformations. So I kind of like these questions. It kind of gives us some real life ideas as to why function transformations are useful in the real world and how we can use different functions to model different items. So if you look at number 1, we're getting started right away with a projectile has a height given by this function. So I like that function notation there, h of t. It's the height as a function of time. It equals negative 4.9 times t minus 4 squared plus 153, where time t is measured in seconds and the height h is in meters. Use transformations to determine the maximum height of the function and at what time it reaches that height, and then confirm your answer graphically. So we're looking at this function here. And what I'd ask you to consider is, what's the original function that's being transformed? Because if we can think about that, we can then think about all the different transformations that occur to this given function right here. So what I encourage you to do is start by thinking about y equals either x squared, or if you want to keep it t, y equals t squared. The original function is something being squared. And we know that the turning point, the minimum value on that graph, starts with a vertex at 0, 0. So what I want to do is I'm going to now list my transformations that can occur to this. And we're going to see where that turning point moves, because that will hopefully get me eventually to a coordinate that represents a maximum height. So let's talk about horizontally what's happening here. Is there any horizontal shifting to the left and right for HRDV? And there is, right? Horizontally, the t minus 4 is going to move us to the right 4 units. So since we're moving to the right 4, the vertex 0, 0 is now at the point 4, 0. Now that I've moved to the right 4 units, is there any reflections happening? And as soon as I see a negative, I know that we're reflecting. So what's going to happen is this graph will reflect over the x-axis. So think about that point at 4, 0 currently. If I take that point and I flip the whole graph over the x-axis, is this coordinate going to change at all? Well, since it's on the x-axis, that point actually stays in place. 4, 0 is still 4, 0. Is there any dilation happening? Are we stretching the graph at all? And the answer is yes, we're stretching the graph according to that 4.9 that's out front. So remember, the negative was the reflection, but the 4.9 is going to be a vertical stretch. And when we do that vertical stretch, we would multiply, since it's a vertical stretch, we would multiply the y values by that 4.9. Well, since my y value is currently 0, that's still going to stay at 4, 0. We're stuck in place. Okay, multiplying y by something, it's not going to affect that value. So finally, we have our v, which is a vertical shift up or down. And we do have a vertical shift in this one. The vertical shift is going to take your final graph and move it up very far. So we're going to move up 153 units so that we finally arrive to the point 4, 153. So right now we know that what happened to this graph? Well, it moved to the right 4, then it flipped over, so now it's an upside down parabola. We stretched it, and then the last thing that happened is you moved it up 153, such that your final graph, might look something like this. I know that's a pretty rough sketch, but I know that that max coordinate is 4, 153. And if we think about what our axes represent here, our x and y axis, our x-axis is really our input of t for time, and then the y-axis represents the height in meters. So the question asks, use transformations to determine the maximum height. Based on these transformations, the max height is 153 meters. And then it says at what time it reaches that height. So the time would be the x value of that point. And it does this after 4 seconds. So it's kind of cool that without even graphing, it says confirm graphically, which you guys can do. You'll have to adjust your window if you want to see this in Y1. Right? You'd have to go up at least as high as 153. But we didn't even need the calculator to determine that. Based on the form that this was given, we can identify the transformations that have been applied and eventually come up with the correct max coordinate there. All right, let's see if we can move on to number 2 and take a look at an archway in the shape of a parabola. Why not, right? I see some parabolic archways sometimes in the world. All right, so we have the equation y equals negative 1/2 x squared plus 10x, where x measures the horizontal distance along the ground and y is the vertical height that the arch is above the ground. Okay, so from this point right here, x is the horizontal distance to this other end of the arch, and then y is the distance above the ground. So here is ground level. We're talking about units of feet here, no longer meters. If that means anything to us, we'll see. The general graph of this arch is shown. Use your calculator to determine the height of the arch at the turning point. So I want to figure out basically how can I adjust my window so I can see that value up there. All right, so we have to probably play around with the window a little bit. We've got negative 1/2 or just 0.5 x squared, and then plus 10x. All right, so from here, what I know is if I go to the window setting, I know that we're really only looking at quadrant 1 here. So maybe instead of negative 10 to 10, I'll go 0 to 10. And then we have to start making some guesses about what the max height is of this archway. So it's in feet above the ground. I mean, I would be, if I were you, try and guess something that's over what you initially think it is at first, in case you're doing an underestimation. Like, for example, if you try 50 feet as the max height of this archway, we're going to find that actually that's almost there. Okay, we're seeing part of this, but I think what we probably would be benefit from doing is extending the x max a little bit further as well, right? Apparently the other end of the arch is more than 10 feet away. In fact, I feel like if I extend it to 20, maybe I'll even increase the y max to 60 in case we're not quite seeing that full max coordinate. That seems like a pretty solid window here. Okay, I can see the entire picture. It looks just like this arch over here. So I made my x max 20 and my y max was 60 to see this. If you have a slightly different window but something very similar graphed there, then you're good to go. But now we can see the turning point. And to determine that turning point, what we can do is a couple different things. I'm going to calculate that maximum value. I don't know how much we've done like this, but if you go to second trace, the calculate menu, we want option 4, which is max. So you need to scroll to the left of the max, hit enter, scroll to the right of the max and hit enter, and then hit enter for the guess. So if you got something like I did here, which says 9.9999999, hopefully you're going to assume that that is at x equals 10, just based on the way the window is set and how far left and right we go. Sometimes we get different, slightly different values there. But this is occurring at 10, 50. And again, the way we got that is we did second trace, which is calculate, and then number 4 was the max. So the question says, use your calculator to determine the height of the arch at the turning point. So the height of the arch at that turning point is it's a height of 50 feet. Okay. Part B, if a second arch was to be created that had the same height but only half the width, determine an equation for this arch. So I want to try and figure out if I were to take half the original width of 20 and cut it down to a width of 10, but I want the height to be the same. I still want that height of 50. How can I adjust my equation such that maybe I'll use this term, horizontally dilate this graph? So what's going to take my x values and essentially cut them in half? Think really hard about that, okay? And I hope what you're thinking about is it's kind of the opposite of what we expect. If you go to your equation originally and you replace every x up here with the quantity 2x, that's going to be a horizontal compression where it cuts your x values in half. So let me go ahead and finish this by plugging in 2x for the other x value here. So if we simplify, I'm going to confirm this on the calculator in a minute that this is correct. But squaring 2x gives you 4x squared. And then 10 times 2x here would be a 20x. Last step, negative a half times 4. You can multiply those coefficients to get negative 2x squared plus 20x. But I'm hoping that's what you thought about, that if we're cutting x values in half, we're not affecting y, right? We need to do that by substituting a 2x in to the original function. And simplifying gets us this result. Let's double check it. If you go to y2 and type in negative 2x squared with a plus 20x after it and hit graph, it should have the same height but half the width. And look how cool we are. We got it without even kind of guessing and checking using the calculator there. Because to be honest, it actually would have been pretty challenging, I think, to guess and check. I don't know, how we would have come up with this result had we not plugged in 2x and then simplified the equation from there, okay? If I wanted it to be not half the width, but twice the width, you would have done the opposite. You would have plugged in a 1/2 x here. Because remember, 1/2 x actually takes your x values and doubles them. It's that opposite effect that we have to really pay attention to there. All right, I want you to think about number 3 on your own. So I'll call number 3 a try it. Okay. This one's just a little bit about even and odd again. So going back to the lesson prior to this. So if you have questions, refer to that. But let's go ahead and read number 4, and we'll do this one together. So in number 4, it says light travels in a straight line and can be modeled by a linear function. When light is reflected off a mirror, it travels in a straight line in a different direction. So you can kind of see this picture over here that when light hits the mirror, it reflects off, and you see the angle of reflection and something according to physics, it's called the angle of incidence there. Thus, the angle of incidence is always equal to the angle of reflection. So you can see those two angles are in fact measured to be the same. And then it says you can use an absolute value function to model this situation. So here's what we're going to do. At a science museum exhibit, I feel like this is something that might happen at like Strong Museum. I feel like this is a thing. A beam of light originates at a point 10 feet off the floor. It is reflected off a mirror on the floor that is 15 feet from the wall that the light came from. How high off the floor on the opposite wall does the light hit if the other wall is 8.5 feet from the mirror? Boy, is there a lot going on here. Let's draw a picture to make some sense of this. So we have a room, okay? And what we know is that the light originates from a point 10 feet off the floor. Okay, so here's the floor. So we're going to start at 10 feet up, and the light's going to come down, and it's going to hit a mirror on the ground. And that mirror is 15 feet from the wall that the light originates from. So this distance is 15 feet. It's going to bounce off, and then it's going to hit another wall. And it says when it hits the opposite wall, this other wall is 8.5 feet from the mirror. So that 8.5 feet, that 8.5 should go in this location right here. What I want to know is how high up the wall will that light reach? So that's what we want to figure out. And since this could be modeled using an absolute value function, we have to pay attention to that piece of it. Let's start defining some things so we can start representing this with an equation. Because if I can represent this with an equation, I actually should know how to find the coordinates at this point. So here's what we've got. I think the best case scenario here is to define this point right at the bottom left corner of my diagram as the origin. I think that's just going to make life easiest. So if I define this point as the origin, we know that the vertex of our absolute value function occurs at 15, 0, because it's 15 units to the right of our origin. So what we know is that we have an absolute value function that's been shifted 15 units to the right. So that would be represented by the absolute value of x minus 15. But what we don't know is, was there any sort of vertical stretching that happened to get the light to be originated from this height of only 10 feet above the ground? So here's how you're going to approach this. We're going to call the scale factor for the vertical dilation, if there is one at all. Let's put an A out front. And to solve for A, what we're going to wind up doing is we're going to choose another point on the graph that we know the coordinate of. How about that point where the light originates? That should be the point 0, 10. If you plug in 0 for x and you plug in 10 for y in this equation, what that will allow us to do is solve for A and figure out, is there some sort of vertical stretch happening here? Because we don't want to assume that this is just a normal absolute value function with slopes of 1 on both sides, like an absolute value typically would have. So plug in 10 for y, plug in 0 for x, and let's solve for A. So we get 10 equals A times the absolute value of negative 15. Remember, absolute value of negative 15 is really positive 15. So to solve for A, you would divide both sides by 15 and get 10/15, which nicely reduces to 2/3. So there is definitely a scale factor. There's a vertical dilation happening here. There's a compression, if you think of it that way, of the original graph absolute value x. Now that I know that, how am I going to figure out how high up the light hits on this wall over here? Well, let's go back and say that we've now defined this function to be 2/3 the absolute value of x minus 15. And what we're looking for is, if I want to know how high up something is, I'm looking for the y value of this point. And in order to find the y value of that point, we would have to know that x value. And I'm hoping we're pretty good to find the x value because it's the total distance, 15, plus that 8.5. So the other wall is 23.5 feet away. And now that I know that x input, we can just come right down here, plug in 23.5 for x, and evaluate this and solve for y. So if you continue this in this part, you can just do in the calculator, right? Type that in, and you're going to wind up getting that 5.6 repeating. Okay, so about 5 2/3 feet would be the height up the wall that the light hits. So kind of a complicated scenario at first. The picture definitely helps us to make some sense of it. The light started here, bounced off the mirror, comes back up. We want to define what I would consider to be a convenient coordinate system. What I mean by that is put the origin in a good location. This way we can easily define where that vertex is. And then once I have the vertex established, we have to decide, is there some sort of scale factor? Is there some value of A that we're multiplying this absolute value function by? Because we have to take that into account. Okay. All right, that's it for me. There is one more question that I'll have you try. It's kind of similar to the last example, so see if you can reason your way through parts A, B, and C in this one. But if you get stuck in any of these steps, let me know and we can go over this. We'll go over this the next time I see you. Okay, so that's a little bit about function transformation application-y type questions. Have a great rest of your day.